Okay, the last new topic we're going to look at is a brief introduction or possibly reintroduction to rotational kinetic energy, because we already talked about it a little bit in terms of why we get mr squared for when we derived our first moment of inertia. But what we want to think about now is something that will end up rolling without slip. So if we have something that rolls without slip, the object will spin around on the surface. So the object will end up moving across the surface and will also roll at the same time. And each one of those provides kinetic energy. And we can end up understanding that that's the case because if we think about something that skids, we could have something that's circular and just moves like this. And if we have something that does that, it still has kinetic energy, it's moving, but it's moving without rotating. We could also have this same wheel, if we ended up lifting it up and spinning it up here, we would get kinetic energy due to the rotation completely separate from sliding. So when we have something that both spins and slides, we end up having a rotational kinetic energy and linear kinetic energy happening simultaneously. And we will end up seeing in the next one some examples where we notice that one of the reasons we didn't talk about something that rolls, we did all these things with these ramps. You probably were looking at it's like, why in the world are we using these blocks? I mean, why? So if I want something to go up a hill, I want to put it on wheels, right? I want it to be spinning. The reason why we didn't is that whenever you have something that spins, we have to worry about the kinetic energy of the rotation in the spinning as well as the kinetic energy of the thing that's sliding along, and that because it's split into both, we end up having two issues. One of them is that the speed we get is less than we might otherwise calculate. The other thing is that not only do you have a different amount of speed, it depends on the geometry of the wheel. So if you end up having something that's, say, a ball that's solid, then we'll end up having a different speed when it rolls down a hill than we would if it was a hollow sphere, which would be different from what you'd get if it was something shaped like, say, a toilet roll. So if it was just all the mass on the outside, it turns out the last one is slowest of all, but we end up getting that by combining those two things together. I gave an example then in this in terms of just advanced looking at it before we delve into it more on next week. For kinetic energy for a solid rolling ball, the kinetic energy would be your translational kinetic energy, 1/2 mv squared. That's always going to be there if it is moving in space. Plus 1/2 your moment of inertia times angular velocity squared. Again, remember this goes back to that, the table we did before, right? So what corresponds to mass is moment of inertia. What corresponds to speed is angular velocity. And for a solid sphere, off the table, again, I'm not expecting you to know it. You get 2/5 mr squared. I actually don't remember which set of tables we had. If you had one on that one where it rotates around the outside like this or rotates through the center, if you just look at a rolling ball, if you slide a ball across, and unfortunately the screen's too small for me to be able to illustrate this very well, if you roll a ball, if you look at where the center of the rotation is, the center of the rotation is through the center of the sphere. And again, you can just slide, anything that's round, you just slide it, and you look at where it's spinning around. It's spinning around the center of there. So that will end up being how I find which one of the moments of inertia, if you've got two of them, it's the one that goes through the center of the sphere. So then your total kinetic energy is the 1/2 mv squared from just sliding, where what would have it just skidded, plus 1/2 times the moment of inertia, 2/5 mr squared, times your angular velocity squared. And remember, in this one on the surface, that the speed on at a radius r is going to be equal to the radius times the angular velocity. And because it's rolling without slip, the speed of the outside rim rotating is the same as the translational speed across. So your r omega is equal to the translational speed. So we can use the same v for both. I mean, the r omega is the speed of the outer surface as it rolls, but that will match the speed this way. So we use the same v. That's the reason why we wrote it that way. Then 1/2 mv squared plus, when you do the arithmetic, 1/5 mv squared gives you 7/10 mv squared. If it was a hollow sphere, then it wouldn't have been 2/5 mr squared, it'd be 2/3. So then we get a different value. 1/2 mv squared plus 1/3 mv squared would be 5/6 mv squared. And if it was, like a toilet paper roll, or something like that, where all the mass is on the outside rim, that it'll be 1/2 times mr squared omega squared. So we have mv squared plus another 1/2 mv squared. So we get a total of 1 mv squared, which ends up being the largest coefficient in front of mv squared we get. In terms of looking forward, just so that you have an idea of what we're going to be getting into, we'll end up talking about kinetic energy and potential energy on the next one. So it's basically energy with rotation. Then we're going to end up introducing angular momentum. And then we'll introduce, in terms of our last major topic, we'll introduce equilibrium, which would include things like how levers work. So we'll end up looking at those sorts of things again. So that gives you sort of a broad feel of what we've got left. All right, then